If you have your take-home thing, you can just set it right here, please. How'd it go? Straightforward? No? A little rough? What was rough?
The second one was annoying.
Annoying? Yeah, I think the second one was annoying. I would agree with that.
I'm pretty sure it's like messing around.
You think so? When you say second one, you mean the center of mass one, right? Not 1B?
Yeah.
Did anybody try 1B?
I don't think
No?
I did.
Okay.
I just typed that into like Wolfram's thing and I didn't even know.
Okay. I might offer 1B as a bonus at some point.
Do you use that like thing that we just learned where you substitute for U and B?
For 1B? No, for 1B, the thing about 1B that's different is that you set up a double integral. Well, you know, I don't want to give it away.
Yeah.
Yeah.
But you wouldn't use that, right? That's
Would not do a change of variables. The integration on that one's a little bit tricky,
okay.
but there's two aspects of 1B that make it a little challenging. One is that your region of integration is different than anything I've ever presented to you. And then the integration is tricky. Those are the two parts that make that problem kind of different. But okay, well, I did have about 4 or 5 students tell me they weren't going to be here today. So if the class looks a little empty, I don't think it's because we had a bunch of people drop, but we'll see. The drop date is this Friday. So if anyone's got questions about their grades or anything, just get with me. All right, so we are in chapter 13, and this is the last chapter of the book. We are going to crawl on our hands and knees to the finish line if we have to. This is a lot of material, all right? Chapter 13 is very dense, so we have 8 class periods left, all right? 9 sections, 8 classes, and 2 sections here require at least a day and a half each. So we are gonna, when I can, we're gonna fly. And when we have to slow down, we'll slow down. All right, but let's get going. 13.1, vector fields. And by the way, chapter 13 is called vector calculus. So we're gonna be doing calculus, but now we're gonna bring vectors into it. Okay, here we go. So let's first define a vector field. Oh, there it is. A vector field in 2-dimensional space. All right, so a vector field in 2-dimensional space. We first have to start out with a domain, a D. So a vector field on D is a vector function, capital F with that little half arrow above it. That's what we use for vectors, right? That assigns to each point x, y in the domain a 2-dimensional vector. So a vector field is a function. It takes in a point, which is an ordered pair, x, y, and it spits out a vector, a 2-dimensional vector, x, y. So you can look at like a magnetic field. So in 2-dimensional space here, you have an invisible magnetic field, but the strength at each point is different. The direction in which these magnetic or these metal filings would be getting pulled is going to be different at every point. So you could look at, pick a point xy somewhere in this xy plane. Pick a point xy and measure the strength of the magnetic field there and what direction it's pulling the metal filing right here. And you could represent that with a vector, right? And every point in this domain is going to have a vector assigned. Understand? Okay. That's an example. Another example would be a topographical map. So you have like a hilltop, all right? And here's kind of a profile side view of that hill. Here's a top view, and we call these topographical maps because these rings represent changes or elevations. So at each ring around this hill represents a fixed elevation. So if we look at this from the top down, right? Here's another topographical map. Then what you could do is imagine this being a two-dimensional XY plane, and for each point you have an arrow, and that arrow would represent the direction of the steepest ascent. Right? Now we actually talked about this before. We called it the gradient vector, but the length of the vector also represents how steep it is. So if it's a very steep at a certain point, you're going to have a very long vector, and if it's not so steep, it's going to be a short vector. You can imagine it also this way. If I take a ball and I just place it at one of these dots, that vector is going to represent which way that ball is going to roll. And again, the length of the vector would tell you how fast it's going to go. Understand? So for each point in this domain, for every point in here, there is a vector for each point. That's a vector field. So here's an example of a vector field. So this time I'm actually giving us the vector function. The vector function is capital F of xy is equal to, now the function is going to spit out a two-dimensional vector. And in this particular example, it's going to spit out negative yx. So what it's going to do is it's going to take in the ordered pair xy. The first component of this vector field is going to be the y-coordinate of the point, but change the sign. And then the y component of the vector is going to be the x-coordinate of the point. All right, so let's see what's happening. What's the vector field doing at the point 0, 0? It's going to give me the 0, 0 vector, which is the 0 vector. So that means at the origin, I should have no vector, right? Nothing. Or the 0 vector, I should say. All right, let's try, how about at 1, 1? Negative 1, 1. How about at 2, 1? Is what? Negative 1, 2, right? So let's actually go out and move this point around. So if I go out to 1, 1, I get the vector negative 1, 1. So remember, vectors are independent of position. A vector can be moved around anywhere, right? If I asked you to graph this vector, I just pulled this marker straight out of the supply closet. You saw me do it, right? Yeah. All right, so if I were ask you to graph that vector, you would go to the left one and up one, and you would draw an arrow, right? But that's this arrow right here. So I am at the point 1, 1. The vector at that point is the vector negative 1, 1. Understand? And if I move to a different position, let me go out to, sorry, that's not what I meant. I meant x-coordinate 2, y-coordinate 1. Then I get this vector negative 1, 2. So it's a longer vector, isn't it? Now I could do this for every single point in this space, right? But if I did that, I'd have vectors everywhere, and you wouldn't really be able to see anything, would you? It would just be vectors everywhere if I were able to go to every point. So what we do is we pick some points to try and get a feel for what's happening here. And let me show you what this vector field looks like. So if you just pick some random points around here, right, and you draw the vectors, it's going to look like that. If I pick more points, you can kind of see that. You get an idea. You almost get this like spinning effect, right? This like looks like if we look at this more like maybe like water on the surface of something, and it's like, what's that water doing? It looks like it wants to turn, doesn't it? And would it be spinning faster in the middle, or would it be spinning faster towards the outside? Should be the outside, because those vectors are longer, right? So the particles out here would be moving faster than the ones inside. Make sense? Okay. Now this is just something where I can make up my own vector field and type it in. So why don't you give me a vector field and I'll type it in here and we'll just see what it looks like. Don't make it all crazy. Just give me something. What do you want? A vector field. What do you want it to be? F of x, y equals, give me the two component functions. And they can both have x's and y's in them. It doesn't have to be like you don't have to separate them. So you want cosine x, sine x? Wait, cosine x, sine x. You don't want y in here at all. That's okay. Sine y? Okay. Let's see what that looks like. Cosine x, sine y. I have to redo this. Hold on. Sine y. All right. That should work. Now let me just see what's happening. What's happening at the origin? Looks like you just have a vector going out the right side. Let's move this along the x-axis. Ooh, whoa, oh. It changed directions, didn't it? Because what's happening to the left and right component here? What does it look like? A cosine function, right? So it's going to go back and forth between 1 and -1, right? Right now, my y-coordinate is 0, isn't it? So sine of 0 is 0. So that's why I'm not getting any up and down. Now let's go ahead and take it up. So if I go up, what's happening? Whoa, look at that. So the y-coordinate is now behaving like a sine function. All right, let's take a look at the field. Wow, okay, that's pretty crazy looking. Okay. It's weird. It's like over here, everything's getting drawn towards like some like weird point right here, right? Everything wants to go here. And then over here, we have something similar, but look, it's like, it like kind of gets pushed away here. And it's strange. This one, look at this one right here. It looks like everything gets pushed away, right? So interesting vector field. Good choice, Saba. Okay, now vector fields can be three-dimensional, right? So if we go back to like looking at the Earth, right? That's the actual visual representation of the Earth's magnetic field. So again, at every point that we pick, there should be some vector that gives you a direction and a magnitude of that field. So in terms of the mathematics, a vector field in three-dimensional space is again a capital F. It takes in an ordered triple, and it returns to you a three-dimensional vector. All right? So here's the vector field. I asked you to sketch this, but I only put that up there because I wanted to have the computer do it. The only way you could really sketch a vector field is to just try and plug in a bunch of points and get a feel for it, right? Like even if we would have used Saba's example and got a bunch of points, I don't think any of us would have come up with that really cool looking picture, right? Do you agree? Like we could have done 50 points and I'm not sure we would have been able to see that pushing away and coming together in the different quadrants. I don't think we would have been able to recover that. But here's a three-dimensional vector field. I'll just go ahead and move a point around. So I'm changing the x, the y, and the z coordinates. And you can see the vector changing as I move. What it's doing is it's taking -y, x, and then 2z. And that's the vector it's spitting out at each point. Let's go ahead and look at the vector field. See what I mean? Like this is impossible for us to really draw and get an idea what's going on. Although from the side, you can kind of see a little, no, that's tough. So look at three-dimensional, it's a lot easier to think about water, like water that's moving. And like if you drop something in there, like where would that particle go? This would kind of tell you like where it's headed. So it's very complicated what's happening in here, right? It's It's very complicated. Okay, so here's another vector field. Negative x over square root of x squared plus y squared plus z squared. Negative y over square root of x squared plus y squared plus z squared. All right. Negative z over square root of x squared plus y squared plus z squared. This is actually the vector field that represents gravitational force. All of these vectors, if you were to take this and find the length of that vector, what would be the length of this vector? You would do that squared plus that squared plus that squared, right? Yes? So if I took the length of this, it would be x squared over that without a root, right? Y squared over that without a root, z squared over that without a root. You put them together because they have the same denominator, and you're going to have x squared plus y squared plus z squared over x squared plus y squared plus z squared. So you're going to get unit vectors no matter what. Any x, y, or z you plug in, you're going to get unit vectors out, right? Yes? Okay. They're all going to be pointing in the same direction. So let me just show you the actual vector field. Let me go in here like that. There, big arrows. They're all center-seeking, right? Center-seeking vectors. And they all have the same magnitude. So this is a good model for gravitational force because now we know that gravitational forces change. You know, it's related to the distance between the two masses. But on Earth, if we're all sitting on the surface, then the gravitational force should be the same. I mean, yes, it's different, but we're not going to get too technical. The Earth isn't even a perfect sphere, right? So we can't even say that, but let's not get too embedded in that. This is good enough for a lot of models, right? This sort of vector field. Okay, now we kind of change gears a little bit here. Talk about what's called the gradient vector field. Recall that if you have a scalar function, notice it's little f, no vector on this. This is a function that takes in two numbers, x and y, and spits out a number, right? This scalar function is a surface, isn't it? If we graph it, this should be a surface. Z equals f of x, y. Now, let's define, or we already defined a couple of sections ago, the gradient of f, which would be, remember that notation? The gradient of f? Which is the vector that is formed by taking the partial derivatives of that function. So the first component is the partial of f with respect to x, and the second component is the partial of f with respect to y. We also have that a function of three variables, we can define its gradient and do the same thing, take partials. In either case, the gradient of little f, or if you write it this way, gradient of little f, defines a vector field, right? Because you give me a scalar function, I can actually come up with a vector field that goes with that function. That vector field is called the gradient vector field. So every scalar function should have a gradient vector field associated with it. So if we are given this scalar function, x squared y minus y cubed, let's find the gradient vector field. So this should be pretty straightforward. Gradient, okay, of f is going to be equal to a vector. Is it two-dimensional vector or three-dimensional vector here? Two-dimensional, so what is it? 2xy, and then x squared minus 3y squared. And that's a vector field, right? I could define this right? I could define that like that. Now, what I'm going to do is I'm going to go back in my notes, and we're going to remember where we could type in the vector fields? I'm going to type that one in, so y'all remember what that is, all right? Actually, I'm leaving it on the board, so I guess we don't have to remember anything. There we go. 2xy. And then the other one is x squared minus 3y squared. There we go. So there's the vector field. Can you all see it? So let's try and understand what's happening here with this vector field. At least a little bit, let's try and understand. I'm going to put some more in here. Maybe I'll make this a little bit bigger. All right, so this is the x-axis, this is the y-axis. What should be happening if I am along the y-axis? If I pick a point along the y-axis, and let's say y is positive, so x is 0, y is positive. If I were to sit there and drop a ball right there, which way is it going to want to go? It's going to want to go towards the origin, isn't it? Now, the further away I am, the faster it's going to want to go, right? Or I shouldn't say it. The gradient, hold on. The gradient is the measurement of the steepest ascent, not descent, okay? So it's actually backwards from what I just said. If I drop a ball here, this arrow points in the direction of the steepest descent. So the ball, if I drop a ball here, it should actually want to roll this way, okay? Because, well, let me bring up the picture and then you'll see what I'm saying. Okay, here's the picture. Here's the picture of the surface, right? This is the original surface that I put in, or that is up there. This is the x-axis. This is the y-axis, okay? So if I were along the y-axis and on the surface, I would kind of be on this back edge. Let me come around this way. Can you all see that? I would be probably somewhere around here, and here's the origin, and this is kind of like the curve of that surface goes down like this. So that vector that we saw pointing towards the origin is giving me the direction of steepest ascent. So if I were to drop a ball here, it would actually roll backwards, and it would be pretty fast that it would roll. Understand? Now, what's happening along the x-axis? If I come in here like this, can you see that side view from the x-axis there? What would happen if I dropped something right here on the x-axis? Which way would it roll? It would looks like it would want to roll to the negative, right? Which means when I look at the gradient vector field, I should have arrows that are pointing the other way. Let's see. Go back to that picture. Did I pass it? I passed it. There we go. So here's my x-axis. Look, see this right here? I've got little arrows that are pointing that way. Now, they're getting bigger. It looks like as I move to the right, they look like they're getting bigger. And you see here in the center, they look really small. And then right here, it looks like we have nothing. So let's go back to that surface. Yeah, I think it's going to be difficult to tell here. But if I'm closer to the origin, there's not as much tilt to that little part along the x-axis. It's not tilted as much, so it's going to be a smaller vector here. But as I move out, look, I've got more of a tilt. You see that? And so my vectors get bigger as I move out. So do you see the important thing to see here is that the gradient vector is telling you something about the shape of this surface. Yes? Okay. All right, conservative vector fields. A vector field is called a conservative vector field if there is some scalar function little f such that the vector field is the gradient of little f. What? All right, so let's go back to the first vector field I gave you. The first vector field I gave us was this vector field right here. Okay? Right? That was our first gradient. That was our first vector field I ever gave you. My question to you right now is this a conservative vector field?
Yes.
Yes? Why?
Because can I use integration to explain?
However you want to explain, yes?
If you integrate that, then it should be a vector field.
You're on the right track because you're saying integration. Look, I'm asking you, is this a conservative vector field? So to say it is means that you must come up with an f. You must find a scalar function f. Right? You need to find that scalar function f. In this case, it needs to be a function of two variables because the vector field is a function of two variables. You must find this scalar function such that when you take the gradient of it, you get this. If you can find a little f that does that, you're in business. You can say it's conservative. So can we do this just by looking? Can you think of something that, remember what these pieces are, okay? This right here, I picked up blue, put down blue and picked up blue. All right, this right here would have to be the partial of f with respect to x, and this would have to be the partial of f with respect to y, wouldn't it? Yes? So can you think of something that would do that? Okay, did someone say it? I heard integration, but does anyone know what the function is? Negative 1/2 y squared.
It'd be negative xy plus c.
Okay, so no, you want, all right. Negative what? Yx plus xy times x? Saba, yes? Do you want me to stop or more? That's it? So what would be the derivative of this with respect to x? Negative y. What would be the derivative of this with respect to y? Negative x. It wouldn't be positive x. We're getting close, though. Do you see this is a little bit challenging, huh? To try and come up with what this needs to be in order for that to happen, yes? Well, here's the thing. In order for a vector function to be considered conservative, you must be able to find a little f, right? This does not say that every vector field is conservative. Not every vector field is conservative. There may not be a little f. It may not exist, all right? Does anyone else have a
Can't it just look two components? Can it have two components?
this? It's a scalar function, so everything has to be a single function. Do we appreciate at least that this is a little challenging to have to kind of reverse engineer this? Yes? Okay, now there's good news. The good news is that there will be a way later on to check very easily to figure out if something is conservative or not. We'll have a test to say thumbs up or thumbs down. But as far as finding it, there's only one way to find it, all right? Well, two ways. You can look and try and figure it out, but we can go through it a more systematic approach. Let's try the systematic approach right now, all right? Let's just try it. I'm going to see if I can't come up with that little f. So let's start with this. Do you agree that little f of xy, or I'm sorry, the partial of f with respect to x must be equal to negative y? Do you agree with that? Yes? Because that's what this says, right? Okay, let's integrate this with respect to x. The antiderivative of the partial of f with respect to x should be equal to the antiderivative of negative y with respect to x, right? I'm just going to take the antiderivative on both sides with respect to x. What should the left side be? Little f, right? So the left side of that should be little f. And the right side of that should be negative xy plus something, right? Now, what about that something? Plus c, right, is what we've always done in the past. But we need to think about this a little bit more. If I put plus c here, it works because when I take the derivative of that, it's going to go away, right? But do you also agree that this could actually have had a y in it? Because if it had a y in it, I would have taken the derivative of it, and it still would have gone away because I would have been taking the derivative with respect to x, right? Look, remember how we got this? We got this by taking derivative with respect to x, right? So let me just say, if this had been y squared over here, then would the derivative of this with respect to x still have been this? Yes, right? So it's possible that this constant over here is more than a constant. It could actually be an entire function of y, but it could not have x's in it, right? So instead of putting constant, I'm going to put g of y. It can be any function of y. Now that function might be a constant, but it could also be y squared. It could be sine y. It could be cosine y, right? Do y'all understand that? Okay, ready? That's what I know about little f so far. Now, let's take the derivative with respect to y of that. And what would happen? If I take the partial derivative with respect to y of this, I get what? Negative x, right? Plus g prime y, the derivative of y, right? And what do we know this needs to be in order for this to work? This needs to be x, doesn't it? So I'm going to put here, but partial of f with respect to y needs to be equal to x. So negative x plus g prime of y must equal x, which means that what? G prime of y must equal 2x, right? We have a bit of a problem now. Because you remember right here at this point where I said that little f could be this plus some function of y, but with no x's in it, right? And we're saying that g prime of y is actually 2x. So what would, if I integrate this, antiderivative of g prime y with respect to y equals antiderivative of 2x with respect to y, what would I get here? What would little g be? I'm going to keep this up here. Little g of y would be what? 2xy, right? Plus some constant. Now this time it can only be a constant. I already said here, right? I said here no x's allowed, right? No x's allowed in this function. And then I went through the work and look what I got as a conclusion. That the only way this works is if g of y is what? 2xy. And it has x's in it, which means what? This is not a conservative vector field. It's not, because I can't come up with a little f that's going to work. Right now, as it sits on the paper, or on the page, we're saying that little f would have to be negative x, right, y, plus g of y, which we said is 2xy, plus some constant. Now take the derivative of that with respect to x. And what do you get? You get negative y, but then here, plus 2y, which gives you y, and that doesn't work. See what's going on here? So it's not possible to come up with a little f, so this vector function is not conservative. Now, if we could, then it would be called conservative. And there's going to be plenty of opportunities to find little f. It's actually a skill that we have to learn, because what I just did there is called partial integration. I did integration on partial derivatives, right? And that plus constant that was actually g of y, we have to pay attention to that when we do partial integration. So more practice to come. I just wanted you to understand the definition first. That's it. We're done. Someone have their book like out? Can I borrow yours real quick?
Careful.
And try not to damage it. Let me just check something here. 760. Yeah, I wouldn't want to have to replenish the book for you here. 21 through 24. Yeah. Okay. This is the homework here. If it says sketch a vector field, like sketch it, just do your best, all right? And on 21 through 24, all they want to do is just find the gradient. So you're just doing partials. There's nothing new here. And now we move on to the next section. All right, this section, extremely heavy in material. We'll get maybe halfway through it. We'll have to come back and do the next half next class. Line integrals, also known as curve integrals. I do not like the title, line integrals, and a lot of people who teach this will agree that the name line integrals in somehow is just bad, because it makes you think that we're integrating over lines or something, that lines have something to do with this, right? It should actually be called curve integrals. So here we go. Suppose we have a function f of xy defined on a curve C in R2. So first of all, f of xy is a surface, right? Yes? But we're going to restrict its domain to a curve in two-dimensional space. Now, surfaces, the ground is the domain, isn't it, on a surface? Yes? Okay, we are only going to allow you to plug points in on the ground that lie on a curve. Take those points and map them up into the surface, as you can see from this picture. So I have a three-dimensional surface, right? There's the surface. This surface is the function on the entire domain, right? But if I restrict the domain just to these points that are on the top half of that circle, those points are on the ground, right? And I plug those into the function, they will be mapped up into the surface, and they will create this blue curve on the surface, right? Okay. Very good. Our question is, if you were to drop a curtain straight down from the blue down to the red, that curtain right there, what's its area? Understand the question? Okay.
So we're not looking for volume?
Not volume. Well, we can't do volume because our domain on the ground is no longer a region. Our domain on the ground is a curve. Yeah, and this is why it gets it's a bad name. This should not be this is a curve integral, it's not a line integral, right? Okay. That's a pretty cool geometric kind of concept, right? I think that's something most people are okay with looking at, like, got it, yes? So how do we do it? Well, let's go back to Cal 2. When we were in Cal 2 and we were doing integrals, we were looking at a two-dimensional picture, weren't we? And when we did this integral, what we did is we imagined cutting this into an infinite number of rectangles, yeah? And when we took that rectangle, they all had the same width, and we called that dx. In the infinitesimal, right, this was our change in x, delta x, but then when we took the limit, it becomes dx. And then the height of the rectangle was what? F of x. And so the area of that whole green thing is the integral, which adds them all up from a to b, right, of the length times width or whatever, f of x dx. And that's the integral from Cal 2, right? We want to have the same concept here. But look, I'm going to take that two-dimensional picture and I'm going to pop this thing out into three-dimensional space. And you can see that's the same picture we have right now. The only thing that's changing in our picture is that this little dx is not going to be the same because this is a line, right? This is a line. They should call this a line integral. This is not curving around on the bottom, right? It's not curving around. And because of that, we can compensate for that by doing the following. Where is it? The first thing we have to do is we have to look at the ground, the domain, and it's going to be some curve in here, right? This is the curve C. In the example I first showed you, I had a red half circle, right? Little half circle on the ground. This curve C. First thing we need to be able to do, we have to be able to draw the curve parametrically. We have to find a way of drawing this where it is a function, or there's only one parameter that controls the drawing of this. And we've done this. We've done this already. When we were doing parametric curves. So we need x to be a function of t and y to be a function of t. So let me try and help you remember one of the most basic ones we had. X is cosine t, y is sine t. What does that draw me? A circle, right? So the x-coordinate is a function of t, the y-coordinate is a function of t. As I plug in values of t, it's going to start drawing me circles, yes? Okay, so when we're doing these line integrals, curve integrals, we first have to get our x and y as parameters of t, or that rely on the parameter t. Then the t will be restricted between two constants. So in other words, let's say that this draws this curve, C, and that x is some function of t, and y is some function of t, and then t is stuck between a and b. Then this point right here would be x of what and y of what? A, right? Because this is the beginning point. I have arrows showing me drawing the curve. I get to here, this would have as an x-coordinate x of b and then y of b. Understand? This, I should have written those like ordered pairs, but do you understand what I'm saying? The x-coordinate is x at a, so I plug a into this, I get something. And then I plug in a to y, I get the y-coordinate, and then same thing here. So it starts and stops, right? You have a starting point and ending point for this curve. And the direction matters, right? Like this particular curve gets drawn starting here and ending here. Okay, I need to continue. Now, back to the picture. Imagine now that I am able to draw this curve on the ground. Okay? Imagine I'm able to draw this curve on the ground. If I can draw that curve on that ground, and I take just a particular little slice of that curtain, okay? I'm just going to take one particular slice of that curtain, and that's going to be a rectangle. Now, how tall is this rectangle? It's the function's value there, isn't it? This is f of xy, right? Because it's a surface, it's two variables going in. But how wide is it? Yes, it is not dx and it's not dy. Instead, what we do is we imagine looking at it from the top like this. Ooh, that's pretty good. That's going to work. It's going to be approximately the length of that hypotenuse. So remember, this direction is x and this direction is y. So this piece right here would be dx and this piece right here would be dy. So the hypotenuse is the length we're looking for, right? And that turns out to be the arc length. And there was a formula for this that we actually got back. Didn't we do this earlier? Yes? So, and in Cal 2 you do an arc length formula. So I'm about to put the formula up here. I just want you to understand why it is we're doing arc length. It's because that piece right there, the bottom of our rectangle, is part of the curve and therefore part of the arc of that red circle. Yes? All right, so here's the formula. All right. First of all, notice the notation here. It's not a double integral. It's a single integral. Integral over C. C is our curve. Of what? The scalar function f of x, y. This is a surface, right? And what am I integrating with respect to here? ds, little s. d little s. This right here means with respect to arc length. When you see d little s. d little x means with respect to x. d little y means with respect to y, right? d little s means with respect to arc length. And so what we do here is we're going to change the integral to go from a to b. Now remember, a and b are the restrictions on t. T is the parameter that draws the x and y coordinates, right? So then I come in here and I replace inside the function, I have to replace x with what? Whatever its function is, right? So that's why I have x of t. And then I replace y with whatever its parametric function is. And then, what is all this? That's the arc length formula. If you have a curve, a parametric curve, this is the formula for the arc length. So you're going to take the derivative of x with respect to t, square it, plus derivative of y with respect to t, square it, take the square root, and then you're going to integrate everything with respect to t. And that is it. This is called the line integral with respect to arc length. All right. Here's an example. Find the line integral of 2 plus x squared y with respect to arc length, where c is the upper half of the unit circle, x squared plus y squared equals 1. So we'll start off by first drawing c. All right, let's draw c. So C is the upper half of the unit circle like this. That's C. And can you come up with the parametric equations that will draw C? Cosine and sine, right? So we're going to go x is cosine t, y is sine t, and t is between where? 0 and pi. That will draw me that C, won't it? Now, I'm gonna rewrite this integral. It's gonna go from a to b, so it's gonna go from 0 to pi. But I need to replace this x with what? Cosine t, and the y with sine t. And ds is actually that square root of the derivatives squared and all that stuff, right? So let's go ahead and do that part over on the side. What would the square root of dx dt squared plus dy dt squared be?
1.
It's going to be 1? It's going to be pretty boring, right? So derivative of cosine is negative sine t. Then I'm squaring that plus derivative of y with respect to t, which would be cosine t, and then squaring that, and that's all 1. And so this is very boring. But clean, right? That's good that that cleaned up. All right, here we go. This is equal to the integral from 0 to pi of 2 plus x squared is cosine squared t times y, which is sine t, and then d what? T, right? Now, it should be 1 dt, but I'm not putting the 1 in there, right? That whole square root thing is just a 1. And so this is just an integral with respect to t now. I think we can do this. Antiderivative of 2 is just 2t. And then this is going to be a basic u sub. Negative 1/3 cosine cubed t. Little chain rule there. Everything works out. And then integrating from 0 to pi. So let's plug in pi. Let's see, pi into here, we get 2 pi minus 1/3. What's cosine of pi? Negative 1, but then cubed, still negative 1. Then times this, so it's going to be plus 1/3. Then subtract, plug in 0. Gone. Cosine of 0? 1 cubed 1, so minus 1/3 in there. Like that. You had to subtract whatever came out. What came out? Negative 1/3. So it's going to be minus minus plus. Put it all together. The answer is what? So this is 2 pi plus 2/3, whatever that is. That is the area. If you were to graph that surface, plug in just the numbers along that circle into that surface, drop a curtain straight down, the area of that would be 2 pi plus 2/3. Make sense? Okay. All right, this is just some technical stuff here. If C is the union of a finite number of smooth curves in C1, C2, C3, all the way to Cn, then the line integral over C of the function with respect to arc length is just the sum of the integrals over each of the curves. In other words, if you have a curve that starts here, goes from here to here, call that C1. And then from that point, maybe that right there, C2. And then here to here, we call that C3. And then here, let's say that's C4. And then if I look at this entire path as being C, the whole thing, then to figure out the line integral, all you're going to do is break it up into 4 different pieces and do each one. Right? Now, the reason why you want to be able to break it up is because you can maybe draw this C1 with a certain parametric equations. But then this C2 is a different set of parametric equations. Then this C3 is a different set of parametric equations. And then this last one. So you would break them up. You'd find parametric equations for each of the curves and then do your math. We're going to do an example. This is just a picture. I have 2 curves. So we're going to find the area that goes from there to there. Whoa. I don't know what this is. Now I'm looking at it. Okay. It should draw them both. Oh, okay, there we go. There's 2 separate curves. So two different areas that you're going to find. You're going to add those up. Okay? All right. Do I not have an example? Thought I had an example. Oh, I did. How did I skip over that? I must have hit that really fast. Okay. Find the line integral of the function 2x with respect to arc length, where C1 is the parabola y equals x squared from 0, 0 to 1, 1, and then C2 is the line segment from 1, 1 to 1, 2. So let's draw this. All right. C1 is the parabola going from 0, 0 to 1, 1. Like that. That's C1. C2 goes from 1, 1 to 1, 2. So that would be just from here straight up, right? That's C2. So imagine that's on the ground. You take just those points, plug them into the surface, and drop a curtain and figure out the area. So let's start with C1. What do I have to do first? I have to find a way to draw C1 using parametric curves. So I need x to be a function of t, and I need y to be a function of t. So how can you draw this parabola?
X of t, t, y, t.
So leave, this will be t and this will be t squared. Let's make sure we all understand that. Whenever you have a function that is solved for y, like this, I'm going to take a couple of examples. These are all functions that are solved. These are solved for y, right? So they're all functions of x. Yes? So whenever you do something like this, you can always just let x be t and y be the function with the x replaced with t. So this would be x is t. This would be y is equal to t squared. This one would be x is t, and then y would be equal to e to the t. Because all you're doing is saying, look, y is e to the t, but what's t? T is x. So this is really e to the x, isn't it? What would you do if you had it the other way around? If x was solved for, if we were solved for x instead of, solved for x instead of y. Then you would go and let what? Y be t and let x be sine t, like that. You would just reverse them. How many of you have the parametric mode? Well, your graphing calculators have a parametric mode. And if you learn how to use your calculator, you can use parametric mode all the time. Because for these, you just do this. And for any others, you can switch them around. Anyway, I'm not going to show you that part. If you want to learn how to use your calculator in parametric mode, I'm happy to show you in my office, not here. Okay, so y'all okay with C1? You got it? All right. What about our restrictions? Our restrictions on Eric? No? T is going to go from 0 to 1. So all you have to do to get that is really just look at, like, if t is x, what are my restrictions on x? And if I'm going to be right here, I'm going to be from 0 to 1. So t must be between 0 and 1. And now I just set up my integral, right? But I'm going to need those derivatives in there, right? Let's go get those derivatives. Let's figure out what the square root of, I'm going to write it this way instead. It's shorter notation. It's not great notation. It's understood here that everyone understands this is the derivative with respect to t. Okay? Here. So what is this? Square root of derivative of x with respect to t is 1 squared is 1 plus derivative of y with respect to t, 2t, but then square it, 4t squared. So I need that for my integral, don't I? Okay. So integral time, integral from 0 to 1 of, don't forget what we're integrating, 2x, right? So that becomes 2t, because we replace x with whatever it was, which was t. And then I still have the arc length part in there, which is root 1 plus 4t squared, and then dt. This one looks like a basic u sub. Just let 1 plus 4t squared be u. The derivative of that's kind of there. We could work through that? Yes? I'm not going to, but yeah? Whatever that you get, that's a number, isn't it? And that would be the area underneath that surface above just C1. Now we need to get C2. So let's do C2. I'll do C2 in blue.